February-March 2022, Paper 4, Variant 2. Question 1. Iodine is found naturally in the compound in many different oxidation states. Most likely is 0 and -1. And the iodide reacts with acidified H2O2 to form the iodines and water. So we know that it's involved acid, and of course the iodides is oxidized by the H2O2 to form these two products. Okay, you can straight away construct the ionic equation. So the H2O2 under acidic condition with iodide, so it's oxidized iodide to this iodine. So because it's -1 to 0, so we say that H2O2 is an oxidizing agent, and of course you have to balance it. Right. So if you're not really sure how to do it, actually you can split this equation into two half equation. Iodides form iodines, release 2 electrons. Okay, after that the H2O2 form H2O. Then you just add the H plus here to balance the hydrogen, and add the electrons to balance the charge. So sum up left to left, right to right. Okay, cancel the electrons, so you get this one. Okay, again, the H2O2 that used in this reaction is oxidizing agent because it's oxidized iodide from -1 to 0. Okay, at the iodines. Part 2. This is a KPC question, which is the easy question. 15 cm cube of this cyclohexane is shaken with 20 cm cube of aqueous solution, and this aqueous solution have the iodines in there. Until no further changes, it's found that 0.39 of iodine is extracted into the cyclohexane, the C6H shaft. After that, the partition coefficient between the cyclohexane and water is given, which is 93.8. So when they tell you it's between the first solvent and the second solvent, so the first solvent is always on top. Okay, the second solvent is always below. So now, the most important information is the KPC, of course. Second important information is the gram. So already 3.939 grams, 0.39 gram of iodine already extracted to this cyclohexane, the organic layer. So now we need to find the mass of iodines that remains in the water layer. So because this one is still unknown, we just, let's say we put X, then we calculate what is this. So in this question, we can straight away use the concentration as gram per the volume. In this case, it's a gram per cm cube. Is alright because it's the same compound, so it's both iodines. So we use gram is enough. No need to convert this one to mole because the concentration of the iodine in this cyclohexane and this iodine is aqueous, so which involve the same solute, right? So you just use gram is enough. Then after that you can use cm cube straight away. You no need to convert to dm cube, so it's meaningless because you're going to cancel it after that. So now just use the KPC expression here. KPC is equal to the concentration of iodine in cyclohexane over the concentration of iodine in the aqueous layer. So 93.8 equal to 0.39 over 15. This is the volume of the cyclohexane used here. So this one is the concentration of iodines in the cyclohexane in gram per cm cube. And now we need to find this X. X is the mass of the iodines that remains in the water layer over the volume of water, which is 20. So rearrange that, so you get this X. 5.54 times 10 power negative 3 gram in there. Part 3. Suggest how the value of KPC of iodine between hexane 2 non with the water now. Just now is a cyclohexane, now is changed to a ketone. First, you need to know the polarity of the solvent. The cyclohexane is a hydrocarbon, is non-polar, and iodine is non-polar compound. So therefore, iodine can dissolve well in cyclohexane because they have the same intermolecular forces, ID. So like dissolve like, so therefore this iodine can dissolve better in cyclohexane. And this ketone is a relatively polar solvent. So therefore iodines will dissolve lesser than, means the amount of iodines will be lesser in this ketone. So what we expect is the concentration of iodine is much lower compared to the cyclohexane because the iodines not really dissolve well in this ketone. Okay, so now we can deduce that what is the Kpc that it should be. So the Kpc, it will be lower. Why? Because the expression, as you can see, if let's say now we change this one to the ketone, so because the concentration now is relatively lower, so the Kpc will be lower too. So that's why Kpc would be lower because the hexane 2 non is more polar than the cyclohexane. So iodine is less soluble in this ketone. Part B. The group 1 iodides all form stable ionic lattice and all soluble in water. Okay, part 1. Define enthalpy change of solution. This one is very easy. So you must write 1 mole of solutes dissolved. Second thing is it must be a sufficient water. We need to make sure the water amount is enough and able to dissolve all these solutes. So make sure all the 1 mole of solutes dissolve well. That's why we need to use a sufficient amount of water. After that, it will, of course, it will form a very dilute solution. Part 2. Table 1.1 giving some this enthalpy change. The first one is the lattice energy. Gaseous ions combined form the solid. So is this the lattice energy of potassium iodide? And this one is the gaseous ion form solution. Gaseous ion of iodide form solution. So both they are titrations enthalpy. So we can use all these enthalpy to calculate the delta H solution, right? Because it's asked to calculate enthalpy change of solution of potassium iodide. It's better for you to construct the H cycle for you to calculate that easier later. Without this also okay. So for this one, you need to know the potassium's gaseous ion and the iodide gaseous ion. So both they can combine and form the potassium's iodide solid. So therefore, this is the lattice energy for this potassium iodide. And the potassium iodide can dissolve in water from this aqueous solution. So this is a delta H solution. And the gaseous ion also can dissolve in water directly. So this will be the hydration enthalpy for this, the cations and the anion, right? So now we try to use this cycle to calculate. So we know that the delta H solution plus the lattice energy, so is equal to this hydration enthalpy. So that's why you get this calculation. So the delta H solution, therefore you get positive 14 kilojoule per mole. Part 3 suggests the trend in the magnitude of lattice energies of group 1 iodide. So from lithium iodide to potassium iodide. Okay, so first you need to know the iodide is actually the same thing for this the trend. So we need to focus more on the cation, means the group 1 cation, from the lithium ions to this potassium ion. So when down the group, as you can see, the size of this or ionic radius of this group 1 cations is larger. Why? Because it has more electron shell, right? So it's larger, and as you can see, the charge for this cation is just positive, same charge. And down the group, we know that volume size is larger, volume is larger, so therefore the charge density is lower. So means the charge in the given volume here is means this one is lesser, means the volume is larger, the charge is still the same. So we say that the density of the charge is lesser or lower. So when the charge density is lower, then the attraction between the cation and the iodide is actually weaker. So what we can expect is the lithium iodide is going to have a stronger attractions between them. Therefore, it will be more exo for this lithium iodide and less exo for this potassium iodide. Right. So this is what you can deduce or predict. So therefore, the answer is lattice energy become less exothermic when it's down the group. So when down group 1, ionic radius become larger, therefore the charge density from lithium to potassium ion decreases. So less or lower charge density, therefore attractions between the cations and ion become weaker. Attraction become weaker means release less energy and therefore is less exo. Part C. The concentration of copper-2 in a solution can be determined by the reaction of copper-2 with iodide, and after that it will form iodine. Then the iodines will further react with the thiosulfate, and the thiosulfate will reduce the iodine back to iodide. So this is a reaction. In this reaction 1 and 2, we try to use the thiosulfate, and this one is to let this iodine or this the brown color disappear. But of course we don't really use this brown color as indicators, so we use the such. So because when the first reaction, iodines form when we put starch, then it will form blue-black. So after the first reaction means when we add the copper-2 and iodide, so the iodines that form immediately will combine with the starch and form the blue-blacks. So when the blue-blacks form, then we try to use the thiosulfate, titrate with the mixture, and titrate until the blue-black disappear. Means when all the iodines has been removed or reacted with the thiosulfate. So when no more iodine, then the blue-blacks will disappear. That's why we use a starch as indicator. So we don't use the brown color of iodines. Now, for the reaction, the volume of the copper-2 solution is 25. So we're going to use this for calculations. And this one reacts with excess iodide. So the end point of the titration means the thiosulfate is 22.3 cm cube of 0.15 mole per dm cube thiosulfate added. So means for this titration it needs this volume. So what you can do now is, okay, first calculate the moles of thiosulfate, use the MV over 1000. After that, you will get the moles of this, and you try to use this mole to get the iodine. So from this equation, we know that the ratio between the iodine and thiosulfate is 2:1. Once you get this mole, so the moles of iodine is therefore half. So that's why you divide by 2. And therefore you get the moles of iodine. So you get the moles of iodine. Then use this mole iodine to get the moles of copper 2. So the moles of iodine is here. Once you get it, compare with copper 2. So copper 2 and iodine is 2:1. That's why here you need to times 2 to get the copper 2, the moles of copper 2. So the mole of copper 2 therefore is what you get here times 2. So you get 3.345 times 10 power negative 3. Actually same as this one. Now, the moles of copper 2 now obtained. We can get the concentration of copper 2 now. So the concentration of copper 2, you can use N equal to MV over 1000. N is a mole, M is a concentration, this is the volume used. This is what we need to get. This one already given, so it's 25 cm cubed. Okay, mole is this one. Therefore, you get this working. 3.345 times 10 power negative 3 times 1000 over 25. So you get 0.1338. Part 2. Identify a suitable indicators for the titration. So I told you already, we use such, right? So until the blue-black gone. No more blue-black, that's the end point. Part 3. Copper 1 and copper 2 both contains electrons in all 5 d-orbitals. In this part, you just need to sketch the shape for this 3dxy. 3dxy, you need to draw the d-orbital, which is the one with 4 loops, and you need to draw the 4 loops between the y and x-axis. So it's not along the axis. Along the axis, for example, like z square, dz square. So there are like 2 loops along the z-axis and the donut ring in between. When you see this xy or xz or yz, means the 4 loops must between the axis, something like this. So you just draw like this, the loops, 4 loops between the y and the x-axis. Right, 1 mark. Part D. The reactions of the iodide ions with persulfate, this is a persulfate, can be catalyzed by the iron 3. So the overall equation is given. Write equations to show how this Fe3 catalyzes the reaction. This one you must start with iron 3, because already told you that iron 3 is a catalyst, means the second equation you must show the iron 3 regenerates. That's the purpose. Now, first, which species will react with iron 3? Positive. So iron 3, after reaction, it must reduce to iron 2. So means it's going to react with the iodide. Because itself get reduced from positive 3 to positive 2, it must oxidize others. So in this overall equation, iodide is being oxidized to iodine. So we must choose iodide. So iodide reacts with Fe3, so it's oxidized to iodine. And of course, Fe3 will reduce to Fe2. Then the Fe2 that produced will use for the second reaction. So Fe2 will react with persulfate, and it will reduce the persulfate to the sulfate ion. So at the same time, the Fe2 will oxidize to the Fe3. So itself get oxidized and is reduced the persulfate to sulfate. Then the Fe3, as you can see, first step is being used, second step is regenerate. Therefore, it's a catalyst. Part E. Oops. An orange precipitate, the mercury iodide, form when the silver 2 ion are added to the mercury 2 ions are added to this potassium iodide solution. The solubility for mercury iodide is this 1 × 10⁻⁷ gram per dm cube. Calculate the solubility product. Solubility product, we must use the concentration in mole per dm cube. Right, so means we have to convert the gram per dm cube here to later to mole per dm cube. All the concentration used to calculate the KSP, so it need to be in mole per dm cube. Molar mass of this mercury iodide is given 454.4. Before you start the calculation, please make sure you do this step. This step is important. The mercury iodide, so it will partially dissolve and form mercury ions and iodide. So it will form, let's say, X mole, dissolves. It will form X mole of this mercury ion, and it will form 2x mole of iodide. That's the concept. So means the just now is told you that solubility of this mercury iodide is this one. Is telling you the concentration of the mercury ions. So how to get the concentration of mercury ion in mole per dm cube? So you use the solubility just now over the molar mass. So because it's gram over the molar mass, so you get mole. Now the concentration of mercury ion, so is 2.201 × 10⁻⁻10 mole per dm cube. So once you get this, then you can get the concentration of iodide, because when X mole of this mercury ions form, it will form 2x mole of iodide. Means the concentration of iodide is double. So substitute these two concentration into the KSP expression. So this one, concentration of this mercury ion times the concentration of iodide square. So the concentration of iodide, remember here, times 2, right? So and square, then you get 4.26 × 10⁻⁻29 mole cube dm -9, right? So this is the unit, right? So because this is mole per dm cube, this is mole per dm cube square, so you get this unit. Okay, that's all. Thank you.